Fluids, pressure, and depth. Some questions to ponder. What factors contribute to pressure within a fluid on Earth? And how does depth in a fluid affect the pressure? Pressure from depth. So, we want to start off here. We talked about how the pressure on Earth varies with depth. The deeper you are, the more pressure you feel. But there's that pesky atmospheric pressure that we want to keep out of the equation for right now. So what we're going to do is we're going to evacuate this cylinder, suck all of the air out of it, and put a tight lid on it so that there's no pressure inside the top part of the cylinder. And we're going to put a fluid, a liquid, in this cylinder here. Could be water, could be anything, could be oil. But we're going to put a liquid in this cylinder, and we're going to support that liquid within the cylinder by this piston underneath it, and that piston is supported by a spring. We're going to use that as a measurement system to measure the weight of this particular liquid. So, a couple other things we need to know here is that the volume of this liquid right here is the volume of a cylinder. So the volume is simply the area of this circle within the cylinder times the height of that cylinder, and that is the volume of our particular cylinder here. And that's important because what we learned about density and mass and the relationship between them is that the density of the liquid times the volume of the liquid will give us that mass, and therefore we can break this down further. The density of the liquid times the area times the height right here, which is the volume, will give us the mass, so that we can equate that to the weight that the spring is holding up here. So finally, the weight of the liquid in the cylinder here is equal to rho times the area, cross-sectional area of the cylinder, times the height of the liquid, the depth of the liquid, times the acceleration due to gravity. So with all that in mind, we can now find the pressure. We did all of this because we knew that pressure was equal to the force per area. So, since pressure is force per area, and the force on this piston down here, this area of this piston, the force on it is the weight of the fluid, we can take that weight, which we broke down here for the fluid, and divide that by the area, and we can see that the areas will cancel out. Therefore, the pressure down here at the piston is equal to the density of the liquid times the depth of the liquid times gravity. Now usually in the equations they're represented in this form, so just switching the G and the H around, we will get our final pressure equation. This is called the gauge pressure, where we get that pressure down here at the bottom of the liquid on the piston. That pressure is equal to the density of the liquid times acceleration due to gravity times the depth of the liquid. Hey, here's a quick question. Let's say I'm in a pool, in our new pool at school, and I'm submerged right up to my neck right here, but I'm in the deep end, so my feet are just kind of dangling, and I'm not touching the bottom or anything. The question is, where would my body feel the most pressure? Up at my chest up here, or down by my toes? Pressure from depth and atmosphere now. We took a look at pressure before and excluded the idea of atmospheric pressure, but if you watch the video on fluids and the atmosphere, pressure in the atmosphere, you realize that the air, when we go all the way out to space there, the air has a considerable amount of mass, and that mass is pressing down on the fluid. So in addition to the weight of the fluid on the piston below here, there's also the atmospheric pressure due to all that air, all the mass of the air in this air column. So if we're going to find out the overall pressure right here, called the total or absolute pressure on at a point right down here at the bottom on this piston, then we have to take our gauge pressure that we derived previously, the density of the liquid times the acceleration due to gravity times the depth of the liquid. So we take that gauge pressure and add to it this atmospheric pressure, which is also pressing down to get our total pressure. Well, hopefully you thought about that answer to our question about being in the pool, and you realized that your feet are deeper than your chest, and therefore, even though you probably wouldn't feel much of a sensation, especially since we sense pressure with our lungs here, probably wouldn't feel a sensation, but the pressure would be greater at our feet because they're deeper than they would be at our chest. Let's look at a graph of pressure versus depth. It makes sense from what we talked about previously that as you get deeper and deeper within a fluid or a liquid, the pressure will increase. And so then on this graph, we also have taken into account that there is the atmospheric pressure. That becomes our y-intercept here. So starting out with that atmospheric pressure, as I pour more and more liquid into a container, at the bottom of the container, as I pour more and more liquid at the bottom of the container, the pressure gets greater and greater the deeper the liquid that is poured in becomes. And that's pretty much our relationship. You can see our linear relationship again. Y is equal to mx plus b here, where the y-intercept is the atmospheric pressure. And the slope in this particular case is the density of the fluid times the acceleration due to gravity. Hey, another quick question. Where would you feel more pressure? If you were 2 meters down in the deep end, right, but not touching the bottom, but close to the bottom of the pool at school, or let's say you were way out in a freshwater lake, in the middle of this huge lake, like Lake Mead, and you were 2 meters down in the lake, where would you feel more pressure? Pascal's vases. This is a picture of Pascal's vases that I got off the internet. The picture shows that the pressure depends on depth and not the volume of the liquid above a particular location. The liquid will all rise to the same level and create a pressure gradient with high pressure at the bottom and low pressure at the top, lower pressure at the top. Of course, there's the atmospheric pressure on all 4 of these open containers. But you can see that the liquid seeks an equal level here. That's because the pressure down here is highest. The pressure at all points at the very bottom here are equal. The pressure right here at the top of this tube are all equal. And you can take any pressure along at any particular depth, and the pressure is going to be the same regardless of the shape of the container or the volume of the fluid above the particular depth. It is simply the depth that determines the pressure. So, hopefully you realized that pressure is really all about depth. And it doesn't matter if you're in 2 meters of water in a swimming pool or 2 meters of water way out in the middle of a lake. You're still 2 meters down and the density of water is still the same. So, whether it being in a pool or being in a lake, it's really the same pressure you'd feel. So, time for a calculation here. What is the pressure at the bottom of a swimming pool that is 2 meters deep? So, if we know what the atmospheric pressure is, wherever that swimming pool is, let's say it's a little bit above sea level at some location, and so it's 95% of 1 atmosphere, and that the density of water is 1,000 kilograms per meters cubed. Pause the video at any point along here and give this problem a go. See how you do on your own before sneaking a peek. So how did he do? It's pretty straightforward. This is our absolute pressure that we're looking for here. That's the atmospheric pressure. And this is the gauge pressure. The pressure due to the liquid at a particular depth and particular density. So our atmospheric pressure isn't a whole atmosphere in this case. It's 95% of 1 atmosphere. So I have to take the 0.95 and multiply by the 101,300 newtons per meter squared, or pascals. Then add to it our density of water times the, we're assuming you're swimming in water, times the acceleration due to gravity times the depth that you were in the pool. And we do those multiplications and add them together, and we get 292,235 newtons per meter squared. Remember, this is a huge amount of force, but it is distributed over a considerable area here of 1 meter squared. A follow-up quick question to those: where would you feel more pressure if you were 2 meters down in that big lake, or if you were 2 meters down in the ocean? Where would you feel more pressure? Well, that was kind of a tricky question. You see, out in the ocean, when you're 2 meters down, it isn't the same as being 2 meters down in a lake, because the ocean water, being salt water, has a greater density. Having a greater density means that you would actually feel more pressure 2 meters down in the ocean than you would in a lake. And if you think about it, it's a lot easier to float in the ocean than it is in the lake. We'll get to those ideas when we talk about buoyancy. E-I-E-I-O. So it's your turn to explore and investigate. Open a tab in your browser and search the following. Let's find out what the pressure is at the deepest part of the ocean, the Mariana Trench. It was just recently explored. Kind of cool. So go pause the video here, open up a tab in your browser, search pressure at the deepest part of the ocean, and see what you find out. So after that, can we answer our questions? What factors contribute to pressure within a fluid on Earth? And how does depth in a fluid affect the pressure? And of course, Scratch has his parting thought. And learning is all about continuous improvement.